very thoughtful, very forward-looking. Our next speaker, Andrew Tsay-Jacobs, is a practicing transit architect at Perkins & Will and is the director of the firm's Building Technology Lab. His research advances an automated and formally flexible AEC future by streamlining the design to fabricate to construction process through robotically controlled oriented digitization. Mr. Jacobs' passion for low to no carbon solutions for the built environment have led him to mass timber as the structural material of choice in his automation research. Andrew is a member of the Ad Hoc Council on Tall Wood Buildings that developed the 2021 International Building Code change that will allow up to 18-story mass timber buildings in the United States. His previous work at Atelier Jean Nouvel investigated alternate structural designs for the MoMA Tower in New York City, and his work at Jacobs Engineering focused on seismic evaluation of FAA structures. Andrew holds a Master of Engineering in Structural Design from the University of Southern California and a Master of Architecture from Columbia University. Andrew.
Hello, thanks for being here, and thanks for that great lecture. It was delightful and terrifying. Yeah. All right, so yes, I was actually invited because we've done a lot of work in the Autodesk build space in Boston. And when Autodesk was asked who they could send or who they'd recommend, they pointed to Perkins & Will because we've done more work there than just about anybody, and a lot of it's been kind of on the robotic end. So in contrast to what was just shared, I want to put out there that robotics is very exciting. And there is this kind of childlike wonder that I think is worth celebrating in this pursuit of progressing AEC into an automated future. This is our roboticist, Hakim Hassan. We have one in the firm. And this expression on his face, to me, is valuable because it says that robotics is a place where we can imagine. And it's a place where we can, robotics forces us to imagine, trying to embrace it, trying to take value out of automation, forces us to be creative. So as architects, it's a great opportunity. One of the prompts, actually, that was given to us as speakers was, what's the uptake in the industry currently of robotics? And this is a map put together by a group called Robots in Architecture, and they've gathered a list. It's not exhaustive, but it's a list of all the creative professionals that have robots and are using them in the design and construct process. It's a very, very long list, and a lot of it's academic. I would say only 20 to 30 of the groups on the list are design focused, actually. They're actually practicing architects or artists, but it's a growing list. I think it's about 100 people are operating robots and claiming it as, this is how we do creative work. So our first foray into robotics was fairly comic. I think it cost us $20,000 or $30,000 to send a couple people to build space to use these very large robots to do something very simple, which was to stretch plastic. And a lot of the kind of first examples of people using robots to do something are very silly. And it takes, I think, in terms of educating a workforce, it takes this first step, making mistakes, and we won't be, at light speed at the beginning. And I think saying to ourselves that this is not a failure, this is an education, took some courage and it took some convincing to our corporate board, but this is where we started. One of the next projects we did was in support of an actual design project that Perkins & Will had. So this is a little pavilion in Vancouver, meant to be a coffee shop that we used as an opportunity to fabricate something for it at Build Space. And we took one of the pedals of this structure and isolated a little scope that we could fabricate. And we broke that little piece down into faceted 2x8s and imagined how we could assemble them together into a panel, which we did. First, we CNC cut all the, we scored actually, it would have been taken too long to cut through the boards. And then by hand, we cut each of the boards. And it's important that I mention this. This doesn't look like robots yet, because it's not. But when we did all this stuff by hand, it was a precursor to what we would do with robots later in a similar mode of design. So these two guys, are slowly picking up one board at a time that they cut, nailing it, screwing it, measuring it, holding it in place. And all of these tasks are just to put 2x4s together, something that's not hard, and it is dull and mundane and potentially dangerous if you put the tool in the wrong place and drive a nail through your hand. So the reason I'm showing you this again is because these things can be automated. So they assembled the panel and then CNC cut it on this large 5-axis mill. Sorry, there's a pop-up here.
We also have the GoPro on the...
And at the end of the day, what we got out of it was just this relic, really, of a process that was very manual. So this is hanging in Autodesk Build Space in a way that says, like, oh, isn't this awesome? But for us, it didn't actually move the needle at all on how you could do something that was custom and needed to be done in a way that's not just stud framing. So, and on that project, there was value engineering done, and the way that the project was actually delivered by the fabricator, I'm sorry, there's some technological thing happening here. I keep having to adjust. It's telling me something about ejecting a USB. I just yank that. Okay. Thanks. So because we didn't have a fabrication partner who had any interest in delivering the project the way we had shown could be done, they went ahead and proposed their own structure, made their own mock-up, and built it that way. That's normal. And the project turned out great. And actually what was useful in our exercise was to show that this crazy geometry of this pavilion wasn't too out there and could be fabricated, even if it ended up being fabricated in a different way. There were some other projects we did at Build Space in support of a few different wood projects. This was a proposal for an 80-story wood tower in Chicago. Always conceived of as just a pie-in-the-sky proposal, but they took it pretty far, the designers, in terms of thinking about how the systems would come together. They worked with Thornton Tomasetti to engineer it, and a researcher at Cambridge to kind of engineer a special type of wood for it. And then the team that was working on it fabricated just a node for it. But again, it was all very manual, and there's another relic that we came up with. We did one space frame out of wood and looked at using the CNC mill to do very precise joinery. Combine all of this with, in parallel, I'm researching mass timber because I believe it's the most sustainable structural material. Instead of putting carbon into the atmosphere, we're putting it into the building. So we put out this book, the Nail Laminated Timber Design and Construction Guide, in 2016. And we worked with a bunch of partners to put this together. And it basically tells you how to build buildings with nail laminated timber, which, if you don't know, it's kind of like cross-laminated timber, only all of the boards are parallel, just like you saw in the previous photos of the curved panel we built. And then I'm on the other side of things, I'm working on code writing. And since I want to be able to build out of wood, and I want the buildings to be of bigger size than 5 stories, we wrote the code to allow 18-story wood buildings. And I'm sure ultimately it'll go higher than that because they can be engineered to be safe, and we did the fire testing to back it up. What does all this have to do with robots? After having completed the first 4 or 5 projects at BuildSpace, we finally felt comfortable again to return to robots and to say, okay, we understand all these other tools, we have a way of working with the BuildSpace and a way of operating and communicating internally. Let's hire a roboticist and let's approach the robot to take on some of the challenges of eliminating manual labor in fabrication. So the main project that I'll share with you for that is the green build pavilion we built robotically out of panels and then assembled on site in Chicago. So that was fabricated in Boston and then trucked to Chicago and assembled manually. So this booth, the premise is that it has to be self-supporting. It can't just be a relic artifact. It has to actually become something that's self-supporting and express a structural logic that could be applicable to multi-story construction. And so the way that this was approached from a robotic standpoint is, how are we going to manipulate the wood? And how will that inform how we design? So the design, there were 2 scripts developed. One is the design script and one is the robotics script. In the design script, we take any surface, could be on sliders and parametric, so it can change any time, and that doesn't slow down our workflow. It doesn't make the robot have to redo anything. If we change the design, the robot will change what it's doing automatically. So this script takes any curved surface, splits it up into a bunch of lines, subdivides those lines into a bunch of facets that approximate the curves, and then applies 2x elements to those facets, and then applies nails to the ends of the board so they all stick together and the nails don't hit each other. This is just a finer grained view of that same thing. And then it puts all that information, the orientation of the boards, the location of all the nails, the sequence in which the boards and the nails go together. It dumps all that into an output file that's all arranged as you'd imagine and very clearly laid out for the next script to pick up. And the robotics script looks at each input as a command to do something. Pick up this board, go cut the board, then put a hole in the board where a dowel will go, then pick up the board again, and each time it has to change a tool. So there is this handoff point between the 2 scripts that has to be very clean, but other than that, everything is perfectly seamless, and no drawings are required, and no 3D model is actually required. We use the 3D model in 2 ways: to visualize for our own satisfaction that this thing looks like what we want it to look like, and to visualize that the robot won't clash and hit something when it's performing its function. So there's not actually a 3D model being used to communicate to any persons. It's for self-satisfaction and for safety. But it's not a part of the fabrication process per se, which gets back to the point about, can we eliminate drawings? Can we eliminate BIM? So I'll play this video. Oh, actually, I should say, developing this work cell, any work cell is always a challenge, and Autodesk helped us get this robot on a track, and then we set up the different tools we wanted to use. And it turned out there were only about 5 tools we needed. I'll play this video. So, is it going to play? So it's pretty fast. There's a few slower ones later, but you can see it just picks up one tool. It's cutting the ends of the board so that all the edges are mitered. And then it picks up the nail gun, and it picks up the next board and repeats the process over and over. It's nice, the guys, Anish and Hakeem were the 2 guys mainly doing this work, and they would go drink a beer while the robot did the work. And there was actually very, very minimal machine tending. As you can see, they're not jumping in the work cell every 10 seconds to do anything. The robot just keeps working until the panel is complete. Okay. Now it's telling me something else is not ejected properly and I can't get out of it. I'm sure you can solve it with the click of one button. Okay, thanks. All right, so let me see. This is one of the simpler roof panels, but some of the panels were pretty large, up to 14 feet. So the shape of the panels, the size, basically, the volume of them, was determined by how much two people could lift. If we were asking robots to lift them, the size would be a lot bigger, or a crane to lift them. But in our case, we had to only have them about 18 inches tall and 3 or 4 feet wide, and then up to 14 feet long. And if you can believe it, 2 guys can pick that up. So then there was the logistical challenge of packing all this stuff. But I'm curious, and one of our next projects is going to be doing this in a site-built way. So assuming you have a foundation poured by whatever means, having the robots assemble this stuff in situ. It's not that much different from building a single-family residence with stud framing. You just automate it. So this is on-site in Chicago, assembling it by hand. But again, if this had been fabricated in Boston, we wouldn't have needed to assemble it by hand because it could have all been assembled by the robot in place. There's a lot of tricky things with gantries and how do you keep the robot climbing up the building. And we haven't tackled those things yet. People loved this and hated it when they saw it. I think most of all, people wondered why we did it, because there wasn't a robot there to tell them what it was about. It just had to be explained. But by and large, the reception was great. People really believed that this can be useful in the real world, partly because it's freestanding. It shows that it's not falling down, and it's not just a mock-up of a panel. It's actually part of a building, if you will. So I'll play this video. This is the whole thing, the whole project in a nutshell. So one of the other prompts for this talk was, what are the trajectories, or where do I see things accelerating? I'll talk about it a little bit more at the end as well, but this project is really about prefabrication. And I think there is a spectrum where robots can apply to specific tasks, or to creating modules, or prefab panels, or to site construction. And I think each of those is a unique problem in a way. I don't think there is a way to talk about all of them as the same thing. You can build a single-family house all on site. You don't have to prefab anything about that. But in affordable housing, multifamily, for example, modularizing a unit and prefabricating panels that are then assembled by robots into units and then brought to site. I think there are incentives to use robots in that entire modularization process. So prefab, panelization leading to prefab modularization, I think, is, for me, the most promising future of robotics that we're following. So, and some of the best practices I just want to mention is that partnering with a fabricator who has the same mind about doing the fabrication process the way we want to is totally important. The project I showed in Vancouver, they weren't on board with how we wanted it to be fabricated in terms of the materiality and how it's put together. But what we're looking at now is finding partners who have robots and are fabricating the way that we want to in a seamless way. In other words, we hand them the outputs of our script, and their robot takes in our outputs as inputs, and it fabricates. That will be an interesting world when we get there, because, like I say, there's no drawings required. The communication is seamless, and there's no loss of information. And those cycles that we saw of loss of information when you transfer from the architect to the engineer to the contractor to the owner, they tend to disappear. So the last thing I want to talk about is MRAD, which is a result of trying to use the robots at BuildSpace and realizing it's very expensive. It's expensive because even though BuildSpace lets us use their facility for free, we have to put people in hotels. And we have to basically keep people in Boston who don't necessarily live there for quite a while. And we decided we should buy our own robot and have it be a mobile robot that can go to each of our offices as needed. So Perkins & Will has over 2,500 employees. We have 26 offices. And it's not practical for each of our offices to have a robot yet. But right now, shipping it from one office to another so that each office can start to get educated on how robotics can change the way we think about design. That's really the goal. So I'll play this video. MRAD is a UR5 robot mounted to a carbon fiber and aluminum frame that assembles and disassembles in an hour. So we designed the platform, and a buddy of mine gave us these Pelican cases to put it into, so we can just hop on the plane with it and take it along. This is, again, Hakeem Hassan, who did the hard work of fabricating the base and programming the robot. So he's bringing it from Boston to LA on this coming Monday, on the way to Autodesk University the following week, where we'll be showing it at the expo. And but previously, we've brought it to a couple of our offices to help with projects, and I'll show you a few of the tools it has and how we're using it. Let's see. Oh, but yeah, actually, this video will show you some of the tools. So you saw some of the tools. A few that weren't shown are the 3D scanner. It actually did show on the screen, the computer screen, the scanned image, but the value of being able to go from digital to physical and then back to digital is pretty exciting to us from an iterative design standpoint. This is a fun tool, just a hot knife, not a hot wire, and we customize the end of the wire in any shape we'd like. The hot wire, obviously, the laser cutter. And there's a couple different ways to glue. We have a 2-stage gluing and single stage, depending on the strength required. The various grippers, suction, and 2-finger. And then the light panel is basically a heliodon. This is just a 3D printed model, but the light panel can show physically what we've been showing for a long time digitally, which is kind of, it's a different feeling to watch the light actually be cast on a model at 2 p.m. at this orientation, yada, 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 than to see it in a computer. What's the business case? That's the question of the hour, right? We don't know. We don't pretend to know. And honestly, we're still in the kind of awe phase, the see what we can do phase. One of the things we did for our Atlanta office, Perkins & Will recently rebranded, we changed our logo, and they wanted a new sign, so we cut out all these foam blocks for them to test out different sizes of signage for them. Another project asked us to mock up some precast panel, fluted wall panel variations, so we did that for them. But none of these little requests, these requests from our offices are not yet the thing that we want them to be asking us for. The thing we are seeking is projects that want us to prototype a process that can be used by a fabricator. If we're just mocking up or making an architectural model, we really missed the. So that's not what we want to be doing long term. But that's what we are doing in the short term while we demonstrate to the designers in the firm how robotics impacts them, how it can impact them, what it can give them, and also to help people start thinking about the limitations of robots and the opportunities of robots, and to put people in the mind of the end effector when they think about design. So I mentioned earlier that affordable housing, to me, is a kind of promising arena for robotics, and I'll explain that a little bit. Perkins & Will historically hasn't gotten into much residential work. We haven't found that to be a profitable way of running our business. But times are changing, and particular to our LA office where I work, we've started to win. There's a huge shortage of housing in LA, especially affordable housing. It's common everywhere in the world, but in LA, what's being done is the city is asking for modular solutions. Specifically, give us your modular solution for affordable housing. And so what we're doing is identifying the opportunities within a floor plan like this to modularize. So it looks like a bunch of, I should say that this building is 70 feet wide, and the module includes 2 units that stretch across the corridor. And what we're interested in doing is finding out ways to automate the mass timber construction, both in the panels themselves and the way they come together. So the use of MRAD in this context is to prototype the way panels come together, the joinery that will be required. And you can scale up a foam model process into the CNC Hundiger process that works for full-scale modules. That's it. Thanks a lot.